Mm. Good evening, everyone, and welcome to this week's session of our webinar series on quantum algorithms using Qniverse. I hope you all enjoyed last week's sessions by Dr. Divyansh on quantum teleportation and super dense coding. It was truly fascinating, and today we have another exciting and interesting session ahead. It's my pleasure to introduce today's speaker, Miss Jivvita, who is currently working at C-DAC Bangalore in quantum technology group. She's focused on quantum error correction. In her work, she has developed and implemented important quantum error correction techniques like repetition code, source code. Uh, we are really looking forward to learning from her expertise today. So, without further delays, let's welcome Miss Jivita as she takes into the world of quantum error correction. Over to you, Jivita. Hello. Yeah.
Uh, I hope I am audible and visible.
Yeah, you are audible and visible.
Okay. Thank you for the introduction. So, good evening, all, and I'll just share my screen. My screen visible?
Yeah, it's visible.
Okay, thank you. Okay, so once again, good evening, everyone. In today's session, I'm gonna talk about quantum error correction. So let's begin. So outline of the session is, first we're going to discuss about classical error correction, and then we're going to dive into quantum error correction. So in quantum error correction, we're going to discuss about two codes. First is the repetition code, and second is the shorts code. So here the bit flip error and the phase flip error comes under one, that is 3-bit repetition code, and then the second code. So now let's start with the classical error correction. So first question which comes to our mind is that why do we need error correction, right? So basically data which will be stored or transmitted are affected by noise and interference. Right now I'm talking about classical error correction. So it is the only possible error is the bit flip. So a single bit flip error can occur where 0 flips into 1 and vice versa. So even a single wrong bit can change the entire meaning of the message. So the goal of this error correction is to detect and correct this error so that we have reliable communications. So for example, I can take you can look into one example where 101, after the transmission it is 100. So where the third bit has flipped from 1 to 0. So this is an error. So the next question which comes to our mind is, can we fix this? So there are many error correction methods, codes in classical also. So today we are going to discuss about simple 3-bit repetition code. Let's begin. So this is the classical version of repetition code. So here the encoding. So encoding is done in a simple manner. So 0 is encoded as 3 copies of 0 and 1 is encoded as 3 copies. So it's quite simple. And how do we detect and correct errors? So if 0 is encoded as 3 copies, then there are 3 possible errors. So error can occur in the third bit, second bit, or first bit, like I've shown here and highlighted. So right now we're just talking about just one error. And here 0 and 1 are called as code words. So from now on, I'll be addressing as code words as well. And after a single bit error occurs, so what do we do now? We detect, and we should detect and correct the error. So detection happens, the logic of detection is also very simple. It is that we do the majority voting. So for example, we can take this, the first example, 2 0 and just 1 1. So the error has occurred in the third bit. So what we do is we just see the majority bits are 0, so we just flip the one bit to 0. It's just simple. So similarly, we do the same thing for the error which occurred in the second bit. So the here also the majority is 0, and we flip the second bit 1 to 0. And in case of the one code word, here the error has occurred in the third bit where 1 has flipped to 0. So we just flip the third bit to 1 based on the majority voting. And this 3 bit, as I told before, it can correct up to one error itself, because if 2 or more error occurs, this code obviously fails. And we have taken the assumption of noise as well. So here it is independent. It means that there is no correlated errors. The error occurring in the third bit is independent of error occurring in the second bit and in the first bit. And what do you mean by identically distributed? The probability of occurrence of error for all the 3 bits are equal. Now let's look into the binary symmetric channel. So here P, where I've considered P is the probability of a single bit flip. So what this means is that uh, this is my bits, and 1 flipping to 0 is of probability P. It means that there has occurred an error, and that the probability of occurrence of that error is P. And 1 remaining in the same state is 1 minus P. The probability of 1 being in error free zone is 1 minus P. And similarly with the case of 0 being in the state of 0, it means that no error has occurred to the bit 0 is 1 minus P. And 0 flipping to bit 1, the error probability is P. Now let's see the possible outcomes, the probabilities of different types of errors. So the probability of there hasn't occurred any error in any of the 3 bits. So we are currently looking at the 3 bit where we have copied 1 bit to 3. We have made a single 0 copies of 3. So in all the 3 bits, the error hasn't occurred. So the probability of that is 1 minus P the whole cube. So we know that the probability of the state remaining in the same state is 1 minus P. So we have 3 bits. We have just multiplied 3 times, and we have. Now the error, the probability of error occurrence is only 1. Only 1 qubit the error has occurred. So that is P into 1 minus P the whole square, and we have 3 bits, so we have multiplied by 3. So this is the error probability of 1 bit, and the remaining 2 bits are in the same state. The error hasn't occurred. And for 2 errors, the probability is as shown here. In this case, this is the probability that 2 bits have error, and this is the probability of just 1 bit the error hasn't occurred in just 1 bit. And for the 3 error, it is the probability is PQ. So this is the error occurred the error occurred which all the error which has occurred in all the 3 qubits, that basically cause logical error. So it means that whatever the qubits we have, all the bits have flipped. So from 0, you can take an example of 3-bit repetition code. So here, basically, if this is the code word, and in this state, all the 3 bits have the error has occurred, it means that this can flip to this code word. And the code words, this is called the logical error, and basically the logical error goes undetected. So whatever error correction code we look into, we try to reduce the logical error rate, because that goes undetectable. I hope you understood the probabilities. Now let's talk about the reliability of 3-bit repetition code. So first, let me talk about the probability of success. So as I told that 3-bit repetition code can correct up to 1 error. So the success rate will be addition of no error, there hasn't occurred any error, and there has been the error has occurred exactly once. So the probability of success is as shown. And the probability of failure. So as 3-bit repetition code fails if 2 or more error occurs. So we calculate 2 error and 3 errors. Since we have only 3 bits, so we consider 2 errors and 3 errors. Now let me take an example. Suppose p is equal to 0.1. It means that the probability of occurrence of error is 10%. So without 3-bit code or without any error correction code, the probability remains the same, because no error has been detected or corrected. There's no error correction code applied. But when we apply 3-bit repetition code, so you just substitute the p in this p fail, and it got reduced to 0.208. It means that the probability of error has decreased from 10% to 2.8%. So of course, this can detect only 1 error, but even then the error probability has reduced. So there is an use for a repetition code. It reduces the error probability. So now we have looked into classical repetition code. Now let's jump into the quantum version of repetition. Let's talk about quantum error correction now. So quantum error correction, it is a crucial field where it aims to protect quantum information and logical information caused by various types of errors, such as noise or environmental noise or decoherence and all. So such as the errors may be bit flips, phase flips, or both. And in quantum error correction, we basically consider poly errors. We actually consider poly errors. So if I can explain about the X error, it is similar to that of the classical version, where the state 0 changes to 1 and vice versa. And in quantum, we have another error which is called the phase flip error, the Z error. So it flips the relative phase between the qubit state plus and minus. So it means that Z error doesn't have effect on state 0, but it flips the sign of state 1. Now let's discuss about bit flip error. So bit flip error, in the bit flip error, so let's discuss how the encoding is done. So this is my logical qubit. This is the information, this contains the information which I want to protect. So what I do is, since we can't basically copy the information, copy the qubits because of no cloning theorem, so what we do is that we take 2 extra qubits. So these are the physical qubits, and we do the entanglement between them. between my logical qubit and between my two physical qubits. So here what is done is that after the entanglement, the information whichever the logical qubit carries, it is distributed among all these three. So at the end of encoding, I can say that these all three contribute to my logical qubit. I have only one logical qubit which is composed of three physical qubits, as all these three qubits contain the information which I need. So at the beginning of the encoding, this will be my state alpha 0 plus beta 1, and after my encoding, this will be my state. So this is called my logical 0, and this is called my logical 1, similar to what we refer to as code words in classical bits. So next what we do is we simulate error. So here in error correction code, we basically simulate error, but in real, errors occur due to various types of noise as mentioned before. You're basically mimicking the effect of noise in the real system by simulating error. So if I take an example, if X error occurs on my first qubit, so whatever the equation I've shown before here, that will be the result. If an X error has occurred in the first qubit, so here 0 has flipped to 1 and 1 has flipped to 0. This will be my state. So next step obviously will be my syndrome measurement, error detection part, which we also known as syndrome measurement. The reason we call it as syndrome measurement because here we introduce two more qubits and we call these as syndrome bits. You can also call them as ancilla qubits. These two are my syndrome bits and we measure only these two bits. I'll explain the procedure, but I'm just telling why do we call it as syndrome measurement. We measure these two syndromes, so that's the reason we call it as syndrome measurement. So now in this, what we do is that I can give an example. So suppose an X error has occurred in my first qubit. So I have applied few C0 gates. So based on this C0 gates, this qubit will be of 1. Because their error has occurred, all this states will be, I'm initializing it to 0. And all the syndrome bits also should be initialized to 0. So this will be 1. And since there hasn't occurred any error, this will be 0. And this will be 0. So I'll tell you how I got this measurement. So what I do is I do the parity check between these two C0 gates. So 1 and 0. 1 and 0, you get it as 1. And here it will be 0 and 0, you get it as 0. Since the target is here, I'm getting the results in this qubit. And the target is this qubit, so I'm getting the result as this. So if an X error occurs in the first qubit, so this will be my measurement, 1 and 0. So 1 and 0, here I've given the table measurement for the syndrome qubits. So 1 and 0, it means that the error has occurred on the first qubit. So similarly with the second, third, and if there hasn't occurred any error. So based on this syndrome measurement, you can easily identify where my error has occurred. All are unique. There's no ambiguity in this. And since we can't measure our logical qubit because it will collapse, so we are just measuring the syndrome bits, and then we are identifying if their error has occurred or not. In case if error has occurred, in which particular qubit based on this measurement. So this is using parity check. And there is also another method which I'm going to explain in the further slides. So I hope this slide you could get. Let me clear. Yeah, so that's how we do the syndrome measurement. Okay, now we have the syndrome table. Let's go through this. So if this is my state, based on this state, based on my syndrome measurement, and apply the recovery operator. So if, as the syndrome table says, 0 and 0, it means that there hasn't occurred any error. So recovery operator, I just apply identity or I don't apply anything. So if the syndrome measurement is 1 and 0, it means that an error has occurred in the first qubit. This is the set. You can just see the bit flip here. 0 to 1 and 1 to 0. So what I do for the recovery is that I apply X gate on my first qubit only. So when you apply this, you get back your error-free qubit. And if the syndrome measurement says 1 and 1, it means that an error has occurred in the second qubit. So you apply X gate to the second, and then you get an error free. So similarly with the third qubit, if the syndrome measures 0 and 1, you get an it means that error has occurred in the third qubit, and you apply X gate, and along with that you get the error free logical qubit. So based on this measurement of the syndrome bits, you identify where the error has occurred, and then you do the operation. Once you do the recovery, you get back to the error free logical qubit. Okay, so now let's dive into a small concept called stabilizer code, which is needed for further slides. So here n represents number of physical qubits and k represents number of logical qubits. So consider S. S is basically a stabilizer group. S is the stabilizer group, which is a subgroup in the group of Pauli matrices. And S contains n minus k elements which all commute with each other. So whatever elements the stabilizer group contains, they all commute with each other. And here minus identity is excluded to maintain positive eigenvalue. So if we define a vector space, so vector space are stabilized by S. S means the stabilizer group. So if I take a state psi, assume the state psi, and you multiply it with G. G is basically a stabilizer. So G belongs to the stabilizer group. It means that G is a stabilizer. We call them as stabilizer. So when we multiply G with this with the state, you can see that the state remains the same. It means that the stabilizer doesn't affect the state if it is error free. So it doesn't disturb the logical qubit at all. So if the state psi has an error in it, G helps, the stabilizer helps to detect the error in the state. So the vector space contains all the states which are stabilized by the stabilizer. It means that it contains all error-free states. So whichever state are stabilized by the stabilizer, they all stay in the vector space and they are error-free. And once you measure, in case assume that the psi in the state psi an error has occurred. So once you measure this, you get a result. That is what the syndrome measurement, what we saw just the previous slide. So that is the syndrome table which you're gonna get after you use the stabilizer to stabilize the state in case there is an error. So I'm going to show you the circuit with the use of stabilizers as well. So let me take an example of the 3-bit repetition code itself. So we saw that it is composed of 3 physical qubits, and these 3 are encoded, these 3 combine one logical qubit. So the stabilizer for the bit flip alone, I'm talking about the bit flip, are Z1, Z2 and Z2, Z3. So one more thing is that we use X stabilizers to measure Z errors, and we use Z stabilizers to measure X errors. So because stabilizers identify the error, we want them to anti-commute basically. So X and Z anti-commute. So if there is occurred an X error, so Z stabilizers can identify it, and vice versa with the Z errors. So when we take an example of this repetition code, so we have seen that 2 to the power k is thus the space has the dimension 2 to the power k. So here the logical qubit is 1. So 2 to the power 1, which gives us 2. So it means that the code, the vector space or the code space contains 2 states. And which are the 2 states? These are logical 0 and logical 1. So these are the error-free states. So these 2 states are present in the vector space. We can just conclude by saying that VS contains all encoded logical qubit states. So whichever the states which are not stabilized by the stabilizer, it means that those states are containing errors. They do not uh, they do not you all understood the stabilizer part. Now this is the same circuit for bit flip, but you can see the encoding is the same, but the only difference is with the syndrome measurement, where in which we saw that we had used X C0 gates. Now here we are using Z gates, CZ gates. So what are we doing is we are using CZ gate to measure, to identify where the error has occurred. So these two circuits, whatever I showed before and this one, are same. You're going to get the same result. It is going to identify X error only, but only the syndrome measurement part is different. Here we are using the stabilizers to identify the errors. There I'm just using the parity, so that it can be of any way, and uh, you can convert this same circuit to the C0 gate. It is both are the same. So we are basically using ZZI and IZZ to identify the errors. So basically Z1, Z2, these two belong to 1, as I told, Z1, Z2, and Z2, Z3, these belong to 1. And since we are not applying any gate to the third qubit, we are assuming it as identity. I mean, we are taking it as identity. So here Z and Z checks the parity between these two qubits. However, I showed earlier the parity check. Here Z and Z checks the parity. So I can take an example. So let's take the syndrome measurement. Whatever you got is 1 and 1. So according to the syndrome table, if it is 1 and 1, an X error has occurred in the second qubit. So when you multiply it with the stabilizer, you pick any of the stabilizer, no need of them. But if a state belongs to the core space, it has to be stabilized by all the stabilizers, not just one, all the stabilizers. So if you take an example of this, and when you multiply this state, which is error, which has error, and when you multiply with this stabilizer, they both anti-commute. So when they anti-commute, that's how we get to know that the state has error in it. Now let's look into the phase flip error. So the phase flip error it is almost, the encoding is almost similar to the bit flip, but what we are adding is, what we are doing extra is that we are adding Hadamard gates to all these 3 qubits. So until here it is the same as the encoding of the bit flip, but since there is a phase flip error, so if it is in the computational basis, it won't be able to detect. So what we are doing is we are applying Hadamard gate. So after this, you're going to get it into the Z basis. So when a noise has been applied to it, so it can easily detect. So at the beginning, alpha 0 plus beta 1, and we apply 2 C naughts to entangle with these 2 qubits. So we are taking again 2 physical qubits, and this is our logical qubit. And after the encoding, all the 3 combined becomes our one logical qubit composed of 3 physical qubits. So at the beginning, this will be our state, and after encoding, this will be our state, alpha plus 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 beta minus minus minus. So after this will be our logical 0. Logical 0 will be represented as this, and logical 1 will be represented as this. Now we do the similar procedure like we did in the bit flip, like we saw in the bit flip error. So here we simulate error again. We are mimicking the real noise. So when we consider that there has been an Z error in the first qubit, so this will be our state. You can see that here plus has flipped to minus, and here minus has flipped to plus. And this is in this plus and minus basis because we have applied Hadamard gate in the encoding section. Next, we do the recovery. So recovery operation, you can say that the syndrome measurement is same as what we saw in the bit flip. But before the syndrome measurement, we are applying Hadamard gate. Just remember that when we did the encoding, it was in plus and minus basis, Z basis, right? So if we are applying C0 gates, it won't be able to detect the error. So what we're doing is we apply Hadamard gate again to convert from Z basis to computational basis. So that in that way, this will be similar to the Z syndrome measurement, whatever we did. So this, after applying Hadamard gate, this will be in computational basis, and when we apply the C0 gates, this will be able to detect the error, where exactly error has occurred based on this table. So this table is same like we saw in the bit flip error. 0 0 means there hasn't occurred any error. 0 1 means error has occurred on the third qubit. 1 0 means error has occurred on the first qubit, and 1 1, it means that error has occurred on the second qubit. So the reason it is 1 1 because there are 2 C naughts which has the control on the second qubit and target as in the first qubit as well as in the second qubit. And after error detection, we apply Hadamard gate as we are converting back to the Z basis, because we have to do the recovery, right? Where after the syndrome measurement, so we apply Hadamard gate, and then according to the syndrome measurement, we apply the Z gate to recover from the error. We apply Z gate to the state. So when we look into the syndrome table, if the measurement is 0 and 0, it means that the state is error free. So we don't apply any operation. And if the measurement is 1 and 0, it means that the error has occurred in the first qubit. You can just see the flip from plus to minus and minus to plus. So for that, to recover to recover the state from this error, we apply Z gate to the first qubit, and after applying this, your state becomes error free. So for 1 and 1, we again apply Z error, because this will be our state, and similar to the third qubit. So based on this table, we apply the recovery operator, and then our logical qubit will be error free. So this is the stabilizer for the phase flip. So here also we do the same. Only the syndrome measurement part will be differing from the previous circuit, but both the circuit will detect Z errors only and will give the same output, similar output. Only the logic is changed here with respect to the syndrome measurement error data. So these are the stabilizers for the phase flip, and x and x check the x tensor x checks the parity between the two qubits. So when we take an example, so this is our syndrome. This is our syndrome measurement 1 and 0. It means that an Z error has occurred in the first qubit. So we basically, what we do, we multiply with the stabilizer and we check where exactly error has occurred. So when we apply this stabilizer, they both commute. Z and I, they commute. So this stabilizer won't be able to detect the error. So according to the stabilizer, there hasn't occurred any error in the state. But as I told, that when a state belongs to the vector space, it means that it has to commute with all the stabilizers, not just one. There might be few exceptions like we saw here. So when we so when we take the second stabilizer, when we multiply with the second stabilizer, then they both anti-commute. So this stabilizer helps to detect the error. So that was all about 3-bit repetition code, about bit flip and phase flip error with respect to 3-bit repetition code. So next, let's go get into shorts code. Shorts 9-qubit code. So here we have 913 code. What do you mean by 9? 9 is the number of physical qubits we use in this shorts code. And we use 9 physical qubits to encode logical qubit, one logical qubit. So there is a number of physical qubits used, there's a number of logical qubit encoded, and this is the number of errors we can detect and correct. So here 3 is the distance. So I can just tell you that. Okay, so this is basically the formula we use. So this is a formula used to check how many errors can be corrected, and this is the formula used how many errors can be detected. So when here d is 3, it means that d minus 1 is 2 by 2 is equals to 1. So in this case, when d is equals to 3, the answer will be 1. So it will be able to detect only one error. Detect and correct. I meant detect and correct. So this represents number of errors it can detect. So here it can, shorts code can detect up to 2 errors. This can detect up to 2 errors if d is equals to 3, and it can correct up to only one error. Okay, so we'll see how the encoding in the shorts code is being done. So this is my logical qubit. First, I start with one qubit, and then basically there are parts in the encoding. First, we call it as phase flip code or outer code, and second, you call it as bit flip code or inner code. So the phase flip code is used for the encoding of the phase one, and the bit flip code is used to encode for the bit flip errors. So since Shor's code can correct any error, any poly error, it means X, Y, or Z. Only one error. So X, Y, or Z. So this is for the phase flip, and this is for the bit flip. So how it is done is that, so first we start with 0, and then we do the phase flip encoding where we convert 0 to plus, and then we do the bit flip encoding where each 0, as plus is nothing but 0 plus 1 by root 2, each 0 state in that will be encoded as 3 other qubits. So I can just tell you here. Okay, just so here plus is nothing but 0 plus 1 by root 2. So here each 0 is again encoded as 3 qubits. So this is the outer encoding, and here each 0 is encoded as 3 bits. So this is the inner encoding. So that's how we're going to get 9 qubits in total, which I'm going to explain in detail in the next slide. So I hope you got an idea about the Shor's code. So this is the circuit diagram for encoding of Shor's code. So here, this is for the phase flip, and this is for the bit flip. Oh, I'm sorry for my drawing skills and writing. So this is for the phase flip, and this is for my bit flip encoding. So first, we start from arbitrary state, alpha 0 plus beta 1. And then we do the entanglement. So this state is very familiar with the 3-bit repetition code encoding, whatever we just saw. So then, since we are applying Hadamard gate to all these 3 qubits, so after applying the Hadamard gate, this will be the state of psi after for the phase flip encoding. Then what we do is we encode each of the plus to again 3 qubits. So since, as I mentioned here, plus is nothing but 0 plus 1 by root 2. So each 0 is again encoded as 3 qubits. Each one is again encoded as 3 ones. So that's how the encoding of the Shor's qubit is done. So when you start with 1, and for the phase flip, you encode it with 3. And at the end of the bit flip encoding, you have 9 qubits in total. So now each plus and minus is 3 physical qubits, giving 9 qubits in total. So after the encoding, all these 9 qubits represent only one logical qubit, which is composed of 9 physical qubits or data qubits. You can call either ways. So at the end, this will be the logical 0 and logical 1. I'll just plug in. Sorry for the disturbance. So when you see the stabilizers for the Shor code, these are the stabilizers to detect bit flip error, and these are the stabilizers used to detect phase flip error. And this is the syndrome table we are using to detect and correct errors. So when an X error has occurred in the first qubit, so Z1 and Z2 will be able to detect this error, so you will get -1. When an X2 error has occurred, so these two stabilizers, since Z2 is present in both the stabilizers, so you'll get minus sign in both these stabilizers. Similarly with other cases. And for the phase flip error, you detect using these two stabilizers. So this is the code for Shor's qubit. So this is the encoding part, and as we have seen, and here I introduce error. You can introduce any error X, Y, or Z. And this is the syndrome measurement for the bit flip error, and this is a syndrome measurement for the phase flip error. And this is the detection part. So here you can see similar pattern like we saw in the repetition code. So you can see the C0 gates of this one, which is similar to that we saw in the phase bit flip and phase flip repetition code. So you can see the same thing, it has repeated thrice, so we basically divided it into 3 blocks. And for the phase flip error, we have seen we can see the similar pattern as well. So where we divide each block into 3 qubits, and the pattern is similar. So I can explain that. Okay, so now you can actually see the similar pattern here. So where this whole block I'm measuring once, and this whole block I'm measuring twice, where target is for 2 different qubits, and the third block I'm measuring once, which is similar to this. So you can say that Shor's code is a extension of repetition code. And then I do the decoding part. After the syndrome measurement, here I've applied X error, simulated X error. So at the end, I'll be applying X to correct it based on the syndrome table. And then I do the decoding and I measure. So that was all about today's session about quantum error correction, where we looked into classical error correction and 3-bit repetition code and Shor's 9 qubit. So now I'll just show you a demo in the Qniverse.
Hello. Hello. Jivvita.
Hello, sorry for the inconvenience. Just give us some 2-3 minutes. She'll come back as she's having some issue with her laptop. Okay.
Hello.
Yeah, Jivvita, you are audible.
I'm extremely sorry. I just got logged out because of connectivity issues. I'll just share my screen. Okay. Is my screen visible?
Yeah, it's visible.
Okay, thank you. Okay, so I was actually about to show you a demo in Qniverse. So let me log in. So once we log in, we have algorithm section where we have all the algorithms. So let me search for repetition code. So here in the input section, we have bit flip, phase flip, and random flip. So I can you can select any of these three options, and you can select in which qubit you want to introduce the error. in Q0, Q1 or Q2. And you load the circuit. So this will be the circuit where this part is what we saw as the encoding part, and here is the error introduced, and this is the syndrome measurement. And you measure only the syndrome bits. Based on the syndrome measurement, you apply the error. So here you can see the probability where 1 1 represents the syndrome measurement, and all these 3 0 represents your logical qubit. So even when an error has introduced, an X error has introduced in the second qubit, but your logical information stays error free because you have detected and corrected the error. So you can just see from the right, you have 3 zeros that represents the logical qubit information. So it is error free. And you can run. And we wait. Okay. So once it has completed, so the probability of 1 1, the result which you get is the measurement of the syndrome, because since you're measuring only the syndrome bits, so you get the result as 1 1, which means that we can see that error has occurred in the second bit. So according to the table which we saw, it means that 1 1 represents error in the second qubit. So similarly, you can try out other errors as well. So I can just show you one more error, which is a random flip. Random flip, it is just random. You don't know where exactly error has occurred. So you can't choose the qubit also to introduce because it is random. And we load the circuit. So since this is random, means it can an X error or Z error can occur. So since there is an Z error, so this is the circuit. This is a circuit for the encoding of the Z, and this is the Z error we have introduced, and this is the syndrome measurement. And at here we are not basically introducing the gate to correct it, but this automatically corrects the error. So we have done a little improvements in this section with respect in this Qniverse. So I can show you Shor's algorithm as well, which I have executed already with respect to X error and Z error. And Shor's algorithm is also available in the Qniverse. You can try it out, which has a random flip. So this will be the Shor's algorithm for the X errors in the specified constraint. We have to introduce the error. If I can minimize it, yeah. So as I've shown you, this is the syndrome measurement as I've explained in the slide for the bit flip, and this is for the phase flip. And this is the decoding part, and this is the measurement part. So when I have to explain it, sorry. So first, I've basically measured the logical qubits, my 9 logical qubits. So here, the first represents my 9 logical qubits. Okay, so these 9 represents my logical qubit, which are 0. It means that my logical qubit is error free. So next, what I have measured is the stabilizers which detect Z error. So Z error, since there hasn't occurred any Z error, so these two qubit remains 0. Next, I have applied X error. So I have applied X error in the 8th qubit. So as I've explained you that there is a block of 3. So this is one block, this is one block, and this is one block. So in the third block, I've introduced an error in the second bit. So basically, you can take it as a version of repetition code. So I've basically applied repetition code 3 times. A block of 3, first repetition code, and a block of 3, second repetition code, and the third block for third repetition code. So according to repetition code, if an error has occurred in the second bit, it means that the syndrome measurement shows 1 and 1. Yeah. So here you get it as 1 and 1. And we have used 6 qubits for measuring the X error, and 2 qubits to measure the Z error. So we have introduced only one error in the 7th qubit. So this represents 1 and 1, and the remaining qubits represent 0, as there hasn't occurred any error. So this was the demo for 3-bit repetition code and shorts code. I hope you all understood, and you can try it out. There are algorithms with different errors, and yeah. So that was all for today's quantum error correction. If any questions, please let me know.
Yeah, thank you, Jivvita, for that wonderful talk. So I think we have some few questions in the chat box. So I will read it out one by one. Maybe you can answer. So the first question is from Ranjan Balajain. He's asking, what are the characteristics of G stabilizer function and how to design it?
Okay, so actually, basically stabilizer code, you design it based on the error correction code you design. So you can take an example for 3-bit repetition code. We have different stabilizers. So whatever the error correction code you design, you can design it on your own. So based on the errors, whichever error you want to introduce in your in your error correction code, based on that you have to design the stabilizers in such a way that the stabilizers are able to detect the error in your qubits, whichever qubit you encode. So for the 3-bit repetition code, you can just take Z1 and Z1, Z2, and Z2, Z3. So 2 stabilizers will be able to detect errors in all the 3 qubits. So
And
based on the code, you will be able to you can design your own stabilizers.
he's also asking how many maximum errors can be detected by the existing methods.
Maximum arrays, I didn't actually get that point.
How many
Maximum
maximum
arrays?
errors? It's errors.
Okay. How many maximum errors? It depends. Again, it depends on the code. So 3-bit repetition code can detect only one error, and shorts it increased to 2 errors. So you can take a surface code which is now in the current booming. It can detect more errors. So it also depends on the code. And if you increase the distance, as I mentioned, increase the distance, then your error correction code will be detectable and will be able to correct more and more errors.
Okay. No. Yeah. One question is, can we get the slides and recording as well? So that is being recorded and it will be available in the YouTube channel of Qniverse as such. It will be available. All the talks, the recorded sessions are available. Naresh, is there anything I am missing out? Any questions you are?
One question is that here the question asked is that do we have an error checksum concept here as well?
Can you repeat the question, sir?
Error checksum concepts are there in quantum error corrections?
As of my knowledge, there hasn't. I have not noted it, but there is parity check, which I explained it. Error checksum might be there. I have not. I don't have much knowledge about that. So that is basically in the classical, which we can find checksum and all.
Yeah,
So
maybe.
parity check we
Yeah,
have.
maybe Hari, if you can put some light onto it.
Hari is saying that we can't have an quantum error checksum concept because of no cloning theorem. So
Okay.
yes. And how many? How to decide the number of physical qubits to be taken, Jivvita?
So how many? How to decide how many?
The number of physical qubits to be taken for doing the error corrections.
Okay, so basically that also depends on your code also. So for the repetition code, you take 3 physical qubits only, and for shorts code you take 9 physical qubits, and you can there's another code called perfect code, which takes 5 physical qubits. So it depends on the logic you want to implement in your error correction code. Based upon that, you can take the number of physical qubits, you can increase or decrease. So it would be better, less number of physical qubits would be better.
Jivvita, I think Hari Krishna, he is asking that how you can say that Shor's algorithm has an speed up. I think maybe he misunderstood that Shor's error correction is similar to Shor's algorithm.
Okay,
Yeah.
this is error correction.
So error correction is different to Shor's algorithm. So Shor's algorithm have an exponential speed up compared to the classical algorithm. So
Yes.
can you throw some light on Shor's error correction? Can we say any speed up for the error corrections?
Speed up, I wouldn't say speed up, but compared to the repetition code, Shor's can correct even Y error, which repetition code was unable to correct. It was able to correct only X and Z error. So Shor's algorithm could correct X, Y, and Z error. But when compared to other error correction codes, which we have right now, such as Steen code, perfect qubit code, it can correct more errors with only less number of qubits. So yeah, Shor's kind of use a larger number of physical qubits to correct it, but these are just the basic error correction codes that we have to understand it, but there are much better and robust error correction codes as well, so we can look into that.
Yeah.
One more thing, Vijay. Actually, Vikas has actually replied for error checksum concept.
Okay.
So what he is saying is that quantum checksum as a set of syndrome bits can be obtained from stabilizer measurements. So that is what his answer for error checksum concept. Yeah, quantum error checksum.
Okay.
Jivvita, I have one more question from my side.
Yes, sir.
So people generally talk about presently they're talking about physical qubits and logical qubits, right? So generally, what is the order? Like for how many physical qubits we'll have some order of logical qubits? Can you just throw some light on that?
Sir, so basically physical qubit, you can have a minimum of 2 physical qubits to encode 1 logical qubit. You can have 3 physical qubits to encode 1 logical qubit. So when you encode, when you take an example of two physical qubits which you can encode into one logical qubit, that can only tell you that if an error has occurred or not. But in your case, when you include three physical qubits to encode one logical qubit, it can able to detect the errors. So number of physical qubits also is important. To decide the number of physical qubits is also important when you are creating your own error correction code.
Yeah, I would like to interrupt. Somebody is asking what's the difference between physical qubit and logical qubit. Maybe that also you can
Yeah.
explain.
Okay. So logical qubit is where our information is confined, and the physical qubits are the things which we take it from state 0, which doesn't have any information. So we have logical qubit which is carrying our data, which the information which we want to protect it. So physical qubits are just, we are adding a qubit from the state 0. These are, you can say it as helper qubits, which are helping to store our information, protect our information. So the logical qubit is the important thing which we want to protect, which carries the information. And once we entangle these logical qubit with the physical qubits, so even since the physical qubits also contain the information after the entanglement, so we consider a specific number of physical qubits to one logical qubit, or whatever your code depends. It can be one logical or two logical, and goes on. Yeah.
Maybe Jivvita, so I just like to comment on that. Now, can we say that, you see, you have a physical qubits, but physical qubits are the qubits which we actually prepare in any kind of system, like superconducting or photonic qubits, but they might be having errors, right? Once we actually reduce the errors using your error correction approaches, what
Yes.
you discussed, and further other advanced, so that we can consider the logical qubits. Am I right?
So yeah, so you're telling that the states which you are preparing contains data.
So qubits, yes. So qubits is quantum data, right? Yes. So when you consider the logical qubits, so whatever the error correction, so whatever the qubits to have certain kind of an accuracy, we call them as in logical qubits. Am I right in thinking in this term?
Yes, sir. The qubit which is carrying data, which we want to protect the data, that we call it as a logical qubit. And physical qubit, we just start it from 0. We just assume that it doesn't carry any information.
So put it in a simple words, it is like the effective qubits available for the user to work on.
Yes, yes.
Yes. So I think no more queries are coming. So it is like we will wind up the session. So thank you for the talk, Jivvita, and thank you all for coming and attending this workshop at this time. So the next week we will be discussing more about the QML based topics in the coming sessions. So stay tuned and we will stop the session. Thank you all.
Thank you so much.